For a long time, humanity has wondered what life on other planets might be like. Thanks to the James Webb Space Telescope, the most sophisticated telescope ever created, we can now start to answer that question. While studying our nearest star system, Proxima Centauri, only 4 light-years away, scientists have detected some unusual phenomena from one of its planets, Proxima B. These phenomena, referred to as artificial lights, have puzzled the leading minds in science. But what could they be? Do these lights suggest the presence of intelligent life on the planet? Join us as we explore James Webb's groundbreaking discovery of city lights that could change everything. Currently, Earth is the only known location of life. Since the dawn of civilization, people have speculated about whether life exists elsewhere in the cosmos. To conduct such an interstellar search, American scientists Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence, SETI project in 1984. The goal of this project is to capture space-based radio signals. Radio waves, which travel further and are less scattered or absorbed compared to other types of radiation, are more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. However, despite 30 years of effort, no verifiable extraterrestrial signals have been found. Subsequently, the successful launch of the James Webb Space Telescope advanced the effort to explore a range of distant, previously unknown planets orbiting remote stars. The world's largest telescope, positioned approximately 1 million miles from Earth and equipped with highly sensitive detectors, is now operational. 20 years ago, there were no known planets beyond our solar system, but today, over 4,000 exoplanets have been discovered orbiting other stars. NASA suggests that there might be trillions of such planets in the universe. The earliest indicators of extraterrestrial life might come from extraterrestrial plant life. When en route to Jupiter, the Galileo spacecraft turned its instruments back toward Earth and detected a definitive sign of vegetation. The instrument identified the vegetation red edge, VRE, biosignature, a blend of red and infrared light reflected by plants. For instance, a planet covered in dense vegetation would emit a strong and easily detectable VRE signal. The JWST will measure the VRE of distant, Earth-like planets within their star's habitable zone. These could be critical indicators of life in an exoplanet's atmosphere. As sunlight passes through a planet's atmosphere, the JWST might detect it. The missing wavelengths in the light would then be identified via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a distinctive fingerprint that the JWST can recognize. This technique might help determine the composition of the atmosphere and the possibility of life. It is probable that life could exist on Earth-sized planets with atmospheres similar to ours, rich in oxygen, nitrogen, and carbon dioxide. Detecting elements not usually present could suggest technological life. Chlorofluorocarbons, CFCs, used in refrigeration and cleaning products would likely be noticeable to aliens observing Earth's atmosphere from afar. If the JWST detected CFCs in a planetary atmosphere, it would be a clear sign of civilization. In reality, life on exoplanets might be vastly different from life on Earth. Sometimes even earthly life, such as extremophiles, can appear alien. Extremophiles are a group of organisms, mostly bacteria, that can survive in extreme environments where other life forms would perish. Some can withstand temperatures up to 250 degrees Fahrenheit. Others can endure as low as -4 degrees Fahrenheit. Some thrive in highly acidic environments with pH levels below 3, while others can be found in seemingly inhospitable places on Earth. However, because planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it makes sense to start with the former. Ideal candidates would have temperatures that allow liquid water to exist on their surfaces and/or orbit a stable star. Our Sun is classified as a yellow G-type star. These stars are relatively rare and typically have shorter lifespans in the universe. Therefore, the likelihood of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. These stars have much longer lifespans, providing more time for life to form and evolve into complex organisms. The TRAPPIST-1 planetary system, located about 40 light-years from Earth, will be one of JWST's first missions. It orbits a tranquil red dwarf star with 7 Earth-sized, rocky planets. 3 of these rocky planets are in the so-called habitable zone, where liquid water might exist on their surfaces. Despite having a much smaller and cooler mass than our Sun, the TRAPPIST-1 star emits light comparable to that of Earth. Proxima Centauri, a red dwarf star situated 4.25 light-years from the Sun, presents the best chance for observing city lights beyond our solar system. Proxima, our nearest star, is about 600 times dimmer than the Sun, so a planet must orbit 20 times closer to it than Earth does to the Sun for it to support life with liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable zone, aptly named Proxima B. Proxima B orbits Proxima Centauri. Given its close proximity to its red dwarf star, Proxima B may be an airless, lifeless world. It orbits at a distance of just 4.6 million miles, compared to the Earth-Sun distance of 93 million miles. Its close orbit exposes it to intense solar winds that could strip away its atmosphere. Nonetheless, it receives enough sunlight to potentially support temperatures and liquid water similar to those on Earth. Proxima B is believed to be tidally locked, always showing the same side to its star, similar to the Moon's relationship with Earth. Proxima Centauri has about 1/8 the mass of the Sun and shines much less brightly than one might expect for a planet so close to its star. A red-hot cinder is to be expected from just 5% of the Sun's distance. Liquid water could easily exist on Proxima B if the planet has an atmosphere to retain heat, as the total energy it receives from its star is only 65% of what Earth gets. However, the planet is not particularly hospitable to life. It is likely tidally locked, creating permanent day and night sides with extreme temperature variations. The planet also receives 100 times more high-energy radiation, including X-rays and ultraviolet light, than Earth does due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flare-ups. Unless it has a protective magnetic field similar to Earth's, its atmosphere may not be sustainable. Models suggest that the atmosphere of tidally locked planets could rapidly collapse due to volatile gases freezing on the night side. Earth's atmosphere is replenished by volcanic activity, and planets with strong magnetic fields are less likely to lose their atmosphere. Since we lack information about Proxima B's volcanic activity or magnetic field strength, we cannot predict whether it has an atmosphere. However, an atmosphere suggests the presence of CFCs, and together they imply the existence of life, making us eager to learn whether Proxima B hosts an advanced civilization. It might have solar panels covering the day side to generate electricity to illuminate and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a race to determine if it crosses its star's face as seen from Earth. Such transits would allow scientists to ascertain the planet's size and mass, enabling them to determine its density. Knowing this would confirm the planet's rocky composition and provide information about the materials that make up its rocks. During a transit, starlight passing through the planet's atmosphere might reveal its nature. However, the chance that the orbit will align properly for scientists to observe a transit is only 1 in 12%. The star's tendency to flare adds further complexity. Astronomer David Kipping from Columbia University notes that the star's heat causes a rocky planet to absorb sunlight and emit it as infrared light. Nevertheless, rocky planets produce a distinctive type of infrared radiation when orbiting stars like Proxima Centauri. Additionally, the James Webb Space Telescope was designed specifically to observe infrared light. The infrared heat signature of Proxima B is crucial for identifying the planet's atmosphere. The infrared spectrum has a strong connection with Hubble's successor, potentially permanently. Researchers will be able to measure water vapor in the atmosphere, determine the abundance of elements like carbon and oxygen, and estimate atmospheric temperature with depth. Using the spectrum that Webb will observe, scientists can draw conclusions about the planet's overall composition and its formation. The best fit model, shown by the blue line on the graph, incorporates the data, the known characteristics of WASP-96b and its star, and the assumed properties of the atmosphere. The modern Webb design allows for exceptionally clear and detailed measurements. The 270-ton, gold-coated mirror effectively captures infrared light. Its sensitive infrared detectors detect minute brightness variations, and its precise spectrographs disperse light into thousands of infrared colors. An IR spectrograph can distinguish brightness differences between colors a few hundred parts per million apart and color differences a few thousandths of a micron apart. It covers infrared light wavelengths never before accessed, which is exciting. Although other telescopes have studied exoplanetary infrared atmospheres, none have achieved this level of detail. This is just a glimpse of what Webb will contribute to exoplanet research. Colin, an expert in exoplanets, notes that Webb's extreme stability, its orbit around L2, and its distance of about 1 million miles from Earth's atmosphere allow for uninterrupted observation and rapid data analysis. The incredibly detailed spectrum, created by analyzing 280 individual spectra simultaneously, represents only a fraction of what Webb will provide. Researchers will use spectroscopy to study the atmospheres of various exoplanets, from small rocky planets to gas and ice giants. Over the coming years, exoplanet research and its associated data will occupy nearly a quarter of JWST's cycle. In one observation, Webb's capability to describe exoplanet atmospheres, including potentially habitable planets, is demonstrated. Most of the science will be conducted through spectra. While pictures are often said to be worth 1,000 words, astronomers consider spectra to be worth 1,000 pictures. Thus, today's episode concludes. We can only hope that the James Webb Space Telescope's mysterious discoveries continue to astonish us with new information about exoplanets. The James Webb Space Telescope, JWST, represents a monumental advancement in humanity's ability to study distant worlds and unravel the secrets of our universe. Launched with the promise of pushing the boundaries of astronomy, JWST is set to revolutionize our understanding of exoplanets, particularly their atmospheres. One of JWST's key innovations is its sheer size and capabilities. With a massive 6.5-meter primary mirror coated with gold to enhance infrared reflection, JWST surpasses its predecessor, the Hubble Space Telescope, in both size and sensitivity. This large mirror enables JWST to gather unprecedented amounts of light from distant celestial objects, facilitating detailed observations previously unattainable. Additionally, JWST is equipped with state-of-the-art instruments designed for high-resolution spectroscopy and imaging across a broad range of wavelengths, especially in the infrared spectrum. This capability is essential for studying exoplanets, as infrared light can penetrate through cosmic dust clouds that obscure visible light, offering clearer views of planetary atmospheres and surface features. One of JWST's primary goals is to perform detailed spectroscopic analyses of exoplanet atmospheres, such as WASP-96b, to detect and characterize key chemical compounds. By observing how starlight passes through an exoplanet's atmosphere during transit, JWST can create transmission spectra that reveal absorption lines corresponding to different molecules, such as water vapor, carbon dioxide, methane, and more. These absorption lines act as unique fingerprints that allow scientists to identify the composition of an exoplanet's atmosphere and infer its physical conditions, such as temperature, pressure, and weather patterns. For instance, the presence of water vapor in an exoplanet's atmosphere could suggest the potential for liquid water on its surface, a critical factor in assessing a planet's habitability. In addition to studying individual exoplanets like WASP-96b, JWST aims to conduct comparative studies of exoplanet atmospheres across different types and sizes. By analyzing a diverse sample of exoplanets, ranging from hot Jupiters to Earth-like planets, scientists hope to uncover patterns and trends that could shed light on the formation and evolution of planetary atmospheres in general. Moreover, JWST's capabilities extend beyond exoplanet research to encompass a wide range of astronomical investigations. The telescope's deep-field observations will probe the early universe, capturing the faint light from the first galaxies that formed after the Big Bang. These observations promise to provide crucial insights into cosmic evolution, galaxy formation, and the origins of heavy elements essential for life. The development and construction of JWST stand as a testament to international collaboration and technological innovation. Led by NASA in partnership with the European Space Agency, ESA, and the Canadian Space Agency, CSA. JWST represents a global effort to push the boundaries of space exploration and scientific discovery. Despite numerous technical challenges and delays, JWST's successful launch and deployment in 2021 marked a historic milestone in space exploration. The telescope's journey to its operational orbit at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, was a test of human ingenuity and perseverance in overcoming complex engineering obstacles. Now fully operational, JWST is ready to embark on a mission of unprecedented scientific exploration. Its ability to look deeper into space and time than ever before promises to revolutionize our understanding of the cosmos and our place within it. From unraveling the mysteries of exoplanets to probing the origins of galaxies, JWST stands at the forefront of astronomical discovery in the 21st century. Looking ahead, JWST's legacy will extend far beyond its initial mission lifespan of 10 years. The data collected by JWST will serve as a treasure trove for astronomers and scientists for decades to come, fueling countless research projects and breakthroughs in astrophysics, planetary science, and beyond. Moreover, JWST's role in inspiring future generations of scientists and engineers cannot be overstated. The telescope's groundbreaking discoveries and captivating images of distant worlds will spark curiosity and fuel dreams of exploration among young minds worldwide. In summary, the James Webb Space Telescope represents a pinnacle of human achievement in space exploration and scientific discovery. With its advanced capabilities and unprecedented sensitivity, JWST is set to uncover the secrets of the universe and reshape our understanding of cosmic evolution. As JWST continues to explore deeper into the cosmos, it holds the promise of revealing new wonders and answering age-old questions about our place in the universe.